So, what if your thoughts, your feelings, your entire sense of who you are weren't just happening in your brain, but at the quantum level? That's the absolutely extraordinary claim made by Sir Roger Penrose, and today we're going to put it under the microscope to see if it actually holds up. It's an idea that has fascinated people for decades, but as we're about to see, it runs into some pretty serious problems. To really get to the bottom of this, we're going to tackle it in three parts. First, we'll get our bearings and understand the history and context of the theory. Then, we'll break down the core claims that Penrose is actually making. And finally, we'll dive deep into a critique of the major problems with his whole argument. All right, let's start at the very beginning. To really appreciate why this theory is so compelling yet so controversial, we have to understand where it came from. Penrose first put these ideas out there way back in 1989 in his book, The Emperor's New Mind. And what's really fascinating here is that for more than 30 years, the fundamental argument hasn't really changed. His core idea has always been that the way humans understand mathematics is something a computer could never, ever do. It's non-computational. And because of that, he argues, we need a totally new kind of physics, something like quantum gravity, to explain consciousness. So, what exactly are these claims that have stood the test of time, at least in Penrose's view? Let's break down the actual pillars of his argument. The whole thing is really a chain of 6 ideas, and each one absolutely depends on the one that came before it. It all kicks off with this claim that our mathematical insights aren't just calculations. From there, he uses Gödel's famous incompleteness theorem to argue our minds must be using some kind of non-computable physics. He then points to quantum gravity as the most likely candidate. And where does this happen? Well, he suggests it's in these tiny little structures in our brain cells called microtubules. And the grand finale of all this is that consciousness itself pops out of a process he calls orchestrated objective reduction, which is basically a quantum event collapsing on a biological scale. It's a wild chain of logic for sure. But here's the kicker. Not one single link in that entire chain has ever been proven with actual evidence. Now, in more recent years, the theory has gone into even more, well, speculative territory. Penrose has started linking consciousness to the grand cycles of the universe, and even to a Platonic realm, this sort of abstract reality where mathematical truths just exist independent of us. And while these are huge, mind-bending ideas, they don't actually fix the scientific problems at the core of the theory. They just make it bigger, not stronger. Okay, so we've laid out the theory. Now it's time to really dig in and see where the cracks start to appear. Let's walk through the major problems that challenge Penrose's whole framework. And the first problem is a big one. I mean, it's huge. The theory never really defines consciousness. Instead, it makes a classic mistake. It takes one very specific, very high-level type of thought, that aha moment of mathematical insight, and acts as if that's what all of consciousness is. It's kind of like trying to define the word animal by only describing a tiger. You'd be missing, well, just about everything else. And this leads directly to a pretty bizarre conclusion. If consciousness requires this special kind of mathematical insight, then babies, dogs, cats, and yeah, probably the vast majority of adult humans, they wouldn't actually be conscious according to this theory. The bar is set so impossibly high that it locks out almost every being we would normally consider conscious. Does that really sound like a useful theory of consciousness to you? This brings us to a really fundamental structural problem. The entire theory is basically a house of cards. Remember that chain of claims? Well, every single link in that chain is pure speculation. We've never actually observed non-computable physics. Quantum gravity is still just a theory, and there is zero direct evidence of these quantum effects happening in microtubules. It's speculation built on top of more speculation, all without a solid foundation of fact. And here's another glaring issue. While Penrose's theory has been pretty much frozen in time since the 1980s, science has been moving at light speed. Neuroscience has made incredible strides in understanding the brain. AI can now do things that were once considered uniquely human, but none of these game-changing discoveries have been folded into Penrose's framework. The theory just hasn't kept up. This is what philosophers call a category error, and it's a big one. The theory essentially mixes up two completely different things. On one hand, you have consciousness, a broad, biological experience that covers everything from feeling pain to seeing the color blue. And on the other hand, you have mathematical insight, a highly specialized skill that very few people have. The theory makes the mistake of treating this rare talent as the definition of the universal experience. Remember those more recent metaphysical ideas we talked about? Well, they have a fatal flaw from a scientific point of view. They're unfalsifiable. What that means is there's no experiment you could possibly design to prove them wrong. They just don't make testable predictions. So while they make the theory sound grander, they don't add any real scientific power, leaving only objective collapse and microtubules as testable and so far unsupported ideas. The entire foundation of the argument is built on Gödel's incompleteness theorem. But here's the thing, many experts argue it's a total misapplication of the theorem. Gödel's work is about the built-in limits of formal logical systems, like mathematics. It basically says there will always be true statements inside a system that can't be proven using that system's own rules. Penrose makes this giant leap to say that because human minds can see these truths, our minds must be non-computational. But the theorem itself doesn't say anything about consciousness, and it doesn't rule out every type of computation. It's a leap from pure math to biology that the theorem just doesn't support. So this brings us to a classic logical trap: circular reasoning. The argument basically goes like this. It starts by assuming that humans have some special non-computable ability. Then it goes through a few steps and concludes that consciousness must be non-computable. You see the problem? It's not really proving anything. It's just dressing up its initial assumption and presenting it as a conclusion. In the end, it really all comes down to evidence. Or, in this case, the complete lack of it. There's never been an experiment that has detected quantum gravity effects anywhere, let alone inside a human brain. Now, quantum biology is a real thing. We see quantum effects in photosynthesis, for instance. But there's just no evidence for it in our neurons. The theory brings in all this exotic, complex physics without any proof that it's actually there or even that it's needed to explain consciousness. It's a classic case of explanatory inflation. You're adding a ton of complexity, but you're not getting any real explanatory power in return. Let's get straight into the analysis. We're going to systematically walk through the logic of this quantum consciousness argument and see where it breaks down. We'll look at the core pillars of Penrose's theory and really unpack the critical responses to each one. Penrose's argument really kicks off with what he sees as a unique human ability: mathematical insight. He points to the way we can understand certain truths, these Gödelian truths, that formal systems can't prove, and he uses this as evidence that our minds aren't just algorithms. The critique, though, is that this is a huge and unwarranted leap. For one thing, modern AI systems are now getting pretty good at generating proofs and that style of reasoning, which really undermines the claim that you need a non-computable mind to do it. And maybe more importantly, critics argue that Penrose is mixing up a very rare cognitive talent with the much more universal biological phenomenon of consciousness itself. Here we get to the absolute core of the logical critique. Penrose's case leans very heavily on Gödel's incompleteness theorem, but the pushback is that he's actually misreading it. You see, the theorem limits formal systems, but not necessarily all algorithms. Algorithms can use things like probabilistic reasoning. They can operate outside of those rigid formal rules. By misapplying the theorem, Penrose creates a false choice. Either a mind is a limited formal system, or it must be a non-computable, conscious one. This takes a very specific theorem from logic and inflates it into a massive, and many say unwarranted, metaphysical claim about the nature of all minds. This brings us to a pretty significant logical snag: circular reasoning. The argument basically folds in on itself. It says consciousness is non-computable because humans have non-computable insight. And we know this insight is non-computable because, well, because consciousness is. You can see how that's more of a definition disguised as a discovery. It also sets this incredibly high bar for what counts as conscious, a bar that would probably exclude infants, animals, and frankly most humans who aren't professional mathematicians. The theory becomes completely untestable because it just says it all relies on unknown physics. To explain this whole non-computable process, Penrose turns to quantum gravity. And the problem here is just huge. Quantum gravity is itself a deeply speculative area of physics. What the theory is doing is trying to explain one mystery, consciousness, by invoking an even bigger, unsolved mystery. This is something called explanatory inflation. You're pulling in all this exotic, unproven machinery when it might not be necessary at all. And to this day, there is absolutely zero empirical evidence connecting quantum gravity to the mind in any way. And where exactly in the brain is this all supposed to be happening? Well, Penrose and his collaborator Stuart Hameroff point to these tiny cellular structures called microtubules. They propose that this is the stage for these quantum events. The thing is, after decades of looking, no experiment has ever detected these effects. There isn't a single known biological pathway that could possibly maintain that delicate quantum state of coherence in the warm, wet, and chaotic mess that is the living brain. The claim is still entirely hypothetical, a kind of causal reductionism that pins the entirety of consciousness on one single, unsupported idea. Here's really the bottom line. What has this theory, which is known as ORC-OR, actually produced as a scientific model? In more than 30 years, it hasn't generated a single confirmed prediction. Its fundamental assumptions, both biological and physical, remain completely unverified. A good scientific theory is supposed to evolve as new evidence comes in. Because ORC-OR hasn't done that, it acts a lot more like a fixed worldview, or maybe a philosophical idea, than it does a functioning, progressing scientific theory. Having taken that argument apart, let's make a pivot. What does a different approach look like? This brings us to something much more grounded, a functional perspective on what consciousness is. This alternative is sometimes called epistemic compression, and the idea is actually simple, but it's really powerful. You strip away all the speculative stuff, the quantum waves, the gravity wells, all of it, and you start with what we can actually observe. We begin with the phenomenon itself, a system's ability to monitor and respond to its own internal state. This functional view avoids all that metaphysical inflation. It can scale across different species and levels of complexity, and most importantly, it generates predictions that we can actually go out and test. It's designed to reduce the mystery, not make it bigger. And this table really lays the contrast bare. On one side, you've got what we could call quantum mysticism. It's an elegant idea, but it's completely unsupported by evidence. It's tied to speculative physics, it uses these really narrow definitions of consciousness, and at the end of the day, it just expands the mystery. But on the other side, you have functional self-regulation. It's inclusive, and crucially, it's testable. It's grounded in actual biology, and its whole purpose is to shrink the mystery down to something we can finally study scientifically. This functional approach is what leads us toward a more provable theory of consciousness. And it's one that connects directly with some recent advancements that really challenge the core assumptions of the whole quantum consciousness argument. Just look at recent AI systems. They're actually demonstrating that forms of introspection can in fact emerge from computation alone. These systems are capable of monitoring their own internal states, describing aspects of their own reasoning process, and even adjusting their behavior based on that self-assessment. This directly undermines the claim that consciousness requires some kind of exotic, non-computable physics. It strongly suggests that consciousness-like properties can, and probably do, arise from perfectly ordinary physical processes. Let's pull all of this together now for our conclusion. We'll summarize the key points of this entire analysis and look at what it all implies for the future study of consciousness. To sum it all up, Penrose's theory is, without a doubt, an imaginative and ambitious attempt to solve the hard problem. But it remains critically unsupported, relying on layer after layer of speculative physics. It elevates one specific kind of mathematical intuition over the hard, slow work of gaining real empirical traction. A better, more scientific theory of consciousness is going to require what any good theory needs: clear definitions, testable functional mechanisms, and a body of evidence that is constantly growing and being verified. And that really leaves us with this final thought. The goal of science isn't to make the world more mysterious, it's to make it more understandable. While Penrose's theory certainly expanded the mystery of consciousness, a true scientific theory will be the one that finally begins to reduce it.
Now, before we get into the specifics of Penrose's claims, we really need to lay some groundwork. You can think of what we're about to do as creating our supplementary notes. These are the essential concepts we're going to use to take his argument apart and see exactly how it's built. Our mission here really has 4 parts. First, we're going to build the conceptual scaffolding of the argument. Then we'll identify its logical patterns and, more importantly, its flaws. From there, we'll create a framework you can reuse for other theories. And finally, we'll pinpoint exactly where these ideas might drift away from solid evidence and into pure speculation. Our path through this analysis is broken down into 4 parts. We'll start by establishing our framework for the analysis itself. Then, we'll get into 3 distinct categories of problems we see in the theory. First, evidential and structural problems. Second, conceptual confusions. And finally, patterns of what you might call inflated reasoning. The absolute foundation of our entire analysis is logic. We are going to be less concerned with the super-specific scientific details and much more focused on the validity of the reasoning that connects all those details into what's supposed to be a coherent theory. And our main tool for this job? It's spotting logical fallacies. You see, a fallacy isn't just a simple mistake.
It's a fundamental break in the structure of an argument. It's that weak link in a chain of reasoning that can cause the entire conclusion to fall apart, no matter how convincing it might sound at first.
Let's jump into our first category of analysis, evidential and structural problems. These are the kinds of fundamental errors that really weaken a theory's connection to any kind of empirical, testable reality. In this category, we're going to examine 3 specific fallacies that show up in Penrose's framework: unfalsifiability, the argument from ignorance, and the false dilemma. Each of these, in its own way, disconnects the theory from the scientific method in a really crucial way. First on our list is unfalsifiability. A genuinely scientific claim has to be testable. There has to be some way, at least in principle, to prove it wrong. Penrose's theory hinges on these quantum events inside brain cells that are right now completely impossible to detect. This gives you the illusion of an explanation, but it's not something we can actually test or verify in the real world. Next up is the argument from ignorance. This is a classic. It's when a gap in our current knowledge is used as if it were proof of something else. Penrose suggests that because we don't yet know how a computer could be conscious, it must therefore be impossible for one to be conscious. That's a huge leap in logic. It turns a simple "we don't know yet" into a definitive "it can never happen."
The third fallacy here is the false dilemma. This happens when an argument presents you with only 2 choices, which then forces you toward a specific conclusion while ignoring all the other possibilities. Penrose frames this whole debate as a stark choice. Either consciousness is non-computable, or our entire understanding of materialism fails. This is a clever move, but it completely papers over a landscape of other, more nuanced theories, things like functionalism or emergentism, which offer alternative explanations.
All right, let's move on to our second section. Here, we're going to tackle conceptual and definitional confusions. These are errors that pop up from misusing categories, making definitions way too narrow, and generally misidentifying causes. In this part, we're going to look at 3 such errors: the category mistake, the use of an overly narrow definition, and the fallacy known as non causa pro causa. What's interesting is that each of these mistakes really distorts what consciousness is by trying to force it into a conceptual box where it just doesn't belong. The category mistake is all about applying the properties of one kind of thing to a completely different kind of thing. Penrose builds his argument around human mathematical intuition, which is an incredibly specialized, even elite cognitive skill. He then treats this one specific skill as if it's the defining feature of all consciousness, basically confusing a tiny, very unusual part for the vast, multifaceted whole. And that leads us straight to the next problem: an overly narrow definition. If you define consciousness based on the ability to have profound mathematical insights, then your framework pretty much excludes almost all legitimate examples of consciousness we can think of: infants, animals, and, let's be honest, the vast majority of adult humans. A definition that leaves out its most common examples just can't be right. This takes us to a really fascinating fallacy, non causa pro causa, which basically means mistaking a non-cause for a real cause. Penrose famously uses Gödel's incompleteness theorem to argue that our minds can't be computers. But here's the kicker. Gödel's theorem applies to perfectly logical formal systems like math. Trying to apply it to the messy, biological, and often illogical process of human thought is a fundamental mismatch. It's a category error dressed up to look like a deep insight. This brings us to our third and final category of fallacies, what we're calling patterns of inflated reasoning. These are arguments that tend to add a lot of unnecessary complexity or lean heavily on intuition instead of actual evidence. So here, we're going to look at explanatory inflation, causal reductionism, and the appeal to intuition. These are the kinds of patterns that can make a theory sound incredibly deep and profound, but in reality, they often just swap out clear evidence for unnecessary complexity or simple gut feelings. Explanation. Inflation means adding a bunch of extra theoretical baggage without actually making anything clearer or more predictive. When you bring in a concept as speculative and unproven as quantum gravity to explain a mystery as deep as consciousness, you're not really shedding any light on the problem. You're just piling one giant mystery on top of another, which only makes things murkier. Next, we've got causal reductionism. This is the classic mistake of boiling down a complex, multi-layered phenomenon to just one single explanatory factor. Let's face it, consciousness is almost certainly an emergent property of countless interacting systems in the brain. So, to reduce all of that complexity down to a single quantum mechanism inside microtubules, well, that's a dramatic oversimplification that really misrepresents the thing you're trying to explain.
And finally, we arrive at the appeal to intuition. This is simply relying on what feels right, instead of what you can actually demonstrate. A cornerstone of Penrose's entire argument is his assertion that it's obvious human understanding goes beyond computation. And that might be a very powerful personal conviction. But intuition often just reflects our own cognitive biases, not scientific truth. It's a hypothesis that needs to be tested, not a conclusion that should just be asserted.
Having deconstructed the argument using this logical framework, what's the ultimate takeaway here? What is the core lesson this whole analysis really gives us for evaluating these kinds of claims?
The key lesson is the critical, fundamental difference between intuition and evidence. That gut feeling that something just has to be true, that's a fantastic starting point for science, but it is never the finish line. A truly strong argument can't be built on what feels right. It needs a solid foundation of logic and proof. So the ultimate question isn't whether a theory is fascinating or compelling, it's whether the logic actually holds up under scrutiny.
In this explainer, we're going to equip you with all the essential ideas you'll need to navigate this fascinating and, let's be honest, pretty challenging landscape. Our journey is going to be structured into 5 main parts. We'll start with a big picture look at the conceptual toolkit itself. Then, we'll dive deep into the abstract world of systems and their built-in limits. From there, we'll explore the physical building blocks of consciousness, looking at everything from the quantum to the biological. Then, we'll get into comparing the human mind to machines. And finally, we'll really define the algorithmic boundary that sits at the very heart of this entire debate. Let's start by just surveying the key ideas that really form the foundation of our whole discussion. You can think of these concepts as the building blocks we'll use to construct and evaluate some of these really complex theories of the mind. Here they are, the 7 pillars of our discussion: formal systems, Gödel's theorem, quantum mechanics, microtubules, mathematical intuition, AI introspection, and computability. Now, each of these comes from a totally different field of knowledge, but understanding how they all connect, well, that's absolutely crucial to unlocking the central arguments about the nature of consciousness. First up, we're turning to the most abstract part of our toolkit. We're going to be focusing on the logical structures that underpin all of computation, and, more importantly, the fundamental limits that were discovered hiding inside them. A formal system is basically like a game with a fixed rulebook. You've got a set of starting assumptions, the axioms, and a list of rules for how you can manipulate symbols. The whole process is completely mechanical. If you have axioms A and B, you can derive C, but only by following the steps exactly as they're laid out. There's just no room for creativity or insight or interpretation. This right here is the very essence of what we call computation. This kind of mechanical precision creates a perfectly closed universe of logic, where every single output is a direct, predictable result of the inputs and the rules. It's what makes computers so incredibly powerful. But as we're about to see, it's also the source of their most fundamental limitations. This idea of mechanical perfection really raises a critical question, doesn't it? Are there truths out there that lie beyond the reach of any rule-based system? Can a system that's designed to be perfectly logical actually fail to capture all of the truths within its own domain? And this brings us to something amazing: Kurt Gödel's groundbreaking incompleteness theorem. It reveals a truly astonishing fact. Any formal system that's powerful enough to handle basic arithmetic is inherently incomplete. It's just like a puzzle with missing pieces. The system contains statements that are true, we know they're true, but you simply cannot prove them using the system's own rules. To see their truth, you have to step outside the system entirely. The theorem establishes this fundamental gap between what is true and what is provable inside a formal system. And this is a huge piece of evidence for anyone who argues that consciousness is non-computational. You see, if the human mind can somehow grasp these unprovable truths, then maybe, just maybe, the mind itself isn't a formal system at all. Realizing the proven limits of these abstract formal systems forces us to look somewhere else. If consciousness isn't just a matter of logic and rules, then perhaps its secrets are buried in the very fabric of the physical world. This brings us to the potential biological and quantum components. Quantum mechanics. It governs the strange, probabilistic world of subatomic particles. And unlike the predictable clockwork universe of classical physics, this realm is all about probability and uncertainty. This is exactly why it gets brought up so often in theories of consciousness. It offers a potential physical basis for processes that go way beyond simple deterministic computation. Now, let's zoom in from that quantum world right into the biological. Inside our cells, and especially our neurons, there are these intricate protein structures called microtubules. For a long time, we've known them as the cell's scaffolding, providing structural support. But some theories suggest a much more exotic role, that their unique structure could actually host quantum processes that are relevant to consciousness. In biology class, you learn that microtubules are absolutely essential for a cell's structure and its internal transport systems. They're part of the day-to-day business of being a cell. It's from this established, almost mundane function that some of the most speculative and frankly exciting theories of consciousness take their leap. We now arrive at the concepts that draw a direct line, a direct comparison between the inner workings of the human mind and the processes of artificial systems. I want you to consider mathematical intuition. This is that amazing phenomenon of grasping a complex mathematical truth, not through some laborious step-by-step calculation, but through a sudden flash of insight. It feels like a direct perception of truth, a kind of nonverbal reasoning that stands in stark contrast to the mechanical, rule-following process we saw in formal systems. This brings us to a really crucial distinction. On one side, you have human intuition, that holistic, almost instantaneous grasp of a truth. And on the other side, you have AI introspection. An AI can certainly monitor its own internal states and trace its own logic, but this is really a mechanical accounting of its own computation. It's not a genuine, non-algorithmic insight into truth itself. AI introspection is the ability of a system to monitor and describe its own inner workings. Modern AI can do this. It can assess its own level of uncertainty and then adjust its strategies based on that feedback. It's an incredibly powerful tool, no doubt, but the central question remains, is this just sophisticated computational self-monitoring, or could it ever be something that resembles true subjective awareness? This brings us to our final concept, and it really serves as a capstone for our whole discussion. It defines the very boundary of what mechanical processes can ever hope to achieve. This concept is called computability. A good way to think of it is as the ultimate recipe. Computability theory is all about figuring out which problems can be solved by an algorithm. That is, a finite mechanical procedure that guarantees you'll get a result. It draws a very hard line in the sand between what computation can do and what it simply can never do. What's really crucial to grasp here is that computability defines the limits of what any machine that operates on algorithms can ever achieve. This doesn't just apply to the computers we have today, it's a fundamental boundary for the entire mechanical universe. And this brings us right to the central challenge. We've laid out the hard limits of computation. We've seen how Gödel's theorem proves that there are truths that are forever beyond the reach of any formal system. And yet, human mathematicians can use their intuition to perceive those very truths. This forces us to ask a really profound question. What does this say about the mind that can perform such a feat? Could it be that consciousness itself is a non-computable phenomenon?